Hi, my name is Mariana Robles, and this is my lab 4 on oscillations. First, this is my table of contents, and we're going to be doing in this presentation. Firstly, the introduction. Observe, analyze, and model oscillatory motion of a spring mass system. We'll choose this using three main tools: Tracker for video analysis, GlowScript for building the computational models of the spring mass system, and simulate its motion and visualize energy transformations over time. Then the spreadsheets for storing data and plugging into the tracker. All this helps us gain a deeper understanding of the bigger picture behind Newton's second law of motion and the effect of Sega force. So let's explore more about this fundamental principle that governs the motion of the object. So the momentum principle states that the net force acting on an object is equal to the rate of change of its momentum over time. In other words, when a force is applied to an object, it changes its momentum, which is the product of its mass and velocity. We can see here by deriving from the momentum principle, we can obtain the velocity update formula. This formula allows us to determine the object's velocity at each time step when dealing with a non-constant force. In our computational model, we use Newton's second law, where the net force is equal to the rate of change of momentum. For a spring mass system, the net force has two parts: the force from the spring and the gravitational force, the equation we can see in this slide. And then the energy principle, which tells us that the energy can be created or destroyed, only transformed from one form to another. In our system, which includes the spring, mass, and Earth, there are no external surroundings doing work or adding heat, so the total energy stays constant. That means the change in total energy of the system is zero. Mathematically, we write that as an equation in this slide, which just means energy moves between kinetic, spring potential, and gravitational potential, but the total doesn't change. We can use this in our GlowScript model to track how energy shifts as the mass moves. We check that the total energy stays constant throughout. For the procedure, we recorded the oscillating spring mass system using the provided video, extracted the X and Y position data using the tracker, and save the data as a CSV file, taking out the time and the headers. And then we imported the CSV file into the GlowScript code that we edited, and we then ran the simulation. Then, to apply this to the lab, we're going to take a look at the actual motion of what we analyzed. Here's a video of the ball being thrown off a table mass hung of a spring oscillating, which we used from our video by examining its motion frame by frame at each of the red diamonds. We can collect trajectory data. With the data collected, we were then able to construct a computational model of the motion we observed. Here are the initial conditions. Before running the simulation in GlowScript, we need to calculate two key initial conditions: the spring constant, K, and the relaxed length of the spring. I used the period of oscillating from the tracker data and plugged it into the formula to calculate the spring constant. And then I calculate the relaxed length using the equilibrium condition where the upward spring force balances gravity. I then plugged both these values into the GlowScript code to make sure the model matches the physical system as closely as possible. Now, in this part of the code, we define the key components that describe the motion and the energy of the system. The first three lines calculate the spring vector L, which goes from the fixed point of the mass. Then we get the unit vector L hat from the spring's direction, and S, which is how much the spring is stretched from its relaxed length. Then below that, we calculate all the system energies at each time step. Here, more calculations. And here too. By running this code, we can get these graphs. Here, we're comparing the motion from our computational model to the actual motion from the tracker video. So on the left, we can see the X position over time. The model and experimental data follows a similar pattern, but there are small differences in amplitude and timing. This can be due to the air resistance, slight camera angle issues, or assumptions in the model like ignoring damping. On the right is the Y position over time, and again, we see a close match in the overall shape, but the experimental position seems slightly more abrupt. This might reflect small inconsistencies in the video tracking or noise in the vertical oscillation. Overall, the trends line up well, which shows that our computational model captures the key physical behaviors of the spring mass system, even though it's not a perfect match. Now let's take a closer look at the possible errors in our experiment and how they may have affected our results. This could be anywhere upwards from human error when conducting video analysis, rounding errors, camera angle misalignment, dismissing external environmental factors, calibration mistakes, measurement errors, modeling limitations. And now for the actual discussion, we are going to reflect over the overall experiment to answer these questions. Is the energy principle satisfied? The answer to that is yes, the energy principle is satisfied. While kinetic, gravitational potential, and spring potential energies vary individually, the change in energy line, the one in orange, stays mostly flat, indicating energy conservation within the system. And then lastly, using the different directions affects spring constant and the final graphs. This highlights how the direction of motion and forces involved affect the observed behavior of the system. Shout out to Cesar.